Now that we've covered synthesis and decomposition reactions, we're going to be moving into our third type of reaction called single displacement or single replacement. So let's take a look at the general equation. We have A plus BC yielding B plus AC. So in this type of reaction, we are always going to have some sort of compound plus an element yielding a new compound and a new element. So if we take a look at this animated GIF, we can see that magnesium bumps silver out of the compound silver nitrate. So you have an element plus a compound yielding a new compound and an element. It doesn't matter whether you write the new compound first and then the element, or the element and then the compound, as long as they're both on the right-hand side of the equation. So when we take a look at our scenario with couples coming together to synthesize, or if they decompose, where they break up, here's a scenario where you have person A with a couple, and person A comes in and bumps out a person from that relationship, and now a new relationship forms, and we have a single individual. So we can kind of think of it like that. Let's take a look at a couple of examples. The first example that I'm going to show you is the reaction between zinc metal and copper 2 sulfate solution. So here we're putting solid zinc metal into an aqueous solution of copper 2 sulfate. And we can see over time there is a slight change that is occurring on the surface of the zinc. Now, it appears as a sort of blackish material initially until it's refined, and that blackish material is solid copper. So let's take a look at what is essentially happening here. In order to get single displacement reactions to work, the compound has to be dissolved in solution. So what that means is it has to become aqueous. Here is blue copper 2 sulfate. It exists as a solid powder. And if I was just to put a strip of zinc metal into that, there would be no reaction. So we have to dissolve the copper 2 sulfate in solution. When that happens, the copper 2 sulfate, being an ionic compound, will separate into its respective ions. So we have all of these mobile ions in solution. We will then put the metal strip into the solution, and then we can get a reaction occurring. So here is what happens. The zinc bumps out the copper from the compound, and then we get solid copper forming, and we notice that there is a change in the color of the solution, indicating that we have aqueous zinc sulfate now being formed. Here is another example of a single displacement reaction. So if I take a piece of solid sodium and I put it in water, I notice that I get a reaction, and the sodium will kind of go along the surface of the water. We can see evidence of some gas being formed there. So we do have a reaction occurring. Now, often people mistake this reaction. This is what should happen. You have sodium reacting with water, forming sodium hydroxide, and there's the gas being formed, hydrogen gas. A lot of people think that sodium reacts with the hydrogen portion of the water and you get sodium oxide. This is incorrect. So whenever water is one of our reactants, sometimes it's better to write water as HOH instead of H2O so that you don't make that mistake. So sodium bumps out this first hydrogen to form the hydrogen gas, and then it hooks up with the hydroxide portion of the water to form sodium hydroxide. So that one is a little bit tricky when it comes to single displacement reactions. So treat water like HOH, and then you won't make that mistake for those type of reactions. Now, here I have a scenario. I've got a whole bunch of different metals: calcium, magnesium, zinc, iron, and gold, and I put them into a solution of aqueous hydrochloric acid or hydrogen chloride. So I notice that I get bubbling with calcium, with magnesium, with zinc, with iron. They're all reacting with that solution, except for gold. So not all single displacement reactions are going to work. And this is where we have to bring in what's known as an activity series. Grade 10, I think you just made the assumption that all single displacement reactions occurred. We have to look at this activity series to indicate whether or not an element has the capability of bumping out another element. So here, when I take a look at calcium, it will be in competition with the metal. We're going to treat hydrogen as a metal. And we notice in this list of metals, we have decreasing reactivity. In order for the metal to bump out another metal in a compound, it has to be higher in this series. So we see that calcium here is higher than hydrogen. So it can bump that out of the compound, hence why you get hydrogen gas forming in this test tube. Magnesium, is it higher than hydrogen? Yes, it is. So therefore, it can bump the hydrogen out. Same with zinc. Zinc is higher than hydrogen. Iron is higher than hydrogen. However, gold is below hydrogen in the activity series. So gold is not more reactive than hydrogen in the compound. So it does not have the capability of bumping it out of solution. Here, let's take a look. We have a single displacement reaction where the element is zinc and it's looking to bump out magnesium. So metals can only bump out other metals. When I take a look at where they are in relation to one another, zinc is below magnesium. So if the element that is looking to bump out the element in the compound is below, it does not have the capability of bumping it out, and we would say that this reaction does not occur. Here, we can also look at nonmetals. So nonmetals would be from the halogen family, and we look at their position relative to one another. Here we have elemental iodine looking to bump out bromine. Nonmetals can only bump out nonmetals. In order to be capable of doing that, it has to be more reactive. So when we look at their position in the periodic table, fluorine is the most reactive nonmetal, and as we move down, they become less reactive. Iodine has to be above bromine in order to bump it out. It happens to be below, so this reaction will not occur, and we say no reaction. Here we have a situation. Chlorine is looking to bump out bromine. Chlorine is above bromine, so this reaction will occur. Let's take a look at a couple other demonstrations so that we can just get an understanding of single displacement reactions. And after you watch this demonstration, you may want to copy these out as well. You should know some applications of single displacement reactions.
Chemical reactions tell us about a metal's reactivity. Mix zinc with copper oxide, lay the mixture out on a heat-proof mat, and heat one end. A reaction soon begins and spreads through the mixture without further heating. Zinc is reacting to form zinc oxide, which is yellow when hot. But what else has formed? Place the remaining solid in dilute acid, and after a few minutes, you can see pure copper. Zinc has reacted with the oxygen in the copper oxide, leaving copper behind. So zinc is more reactive than copper. Aluminium is another reactive metal. Its reaction with iron oxide gives out a huge amount of energy. A measured amount of aluminium is mixed with iron oxide and placed in a small pot. Potassium permanganate is sprinkled on top, and glycerol is added. The vigorous reaction between potassium permanganate and glycerol gives out enough heat to start the main reaction. Red hot molten iron falls into the bucket. The aluminium has reacted with the oxygen in the iron oxide, leaving iron metal behind. So aluminium must be more reactive than iron. This reaction is so effective that it's used on a larger scale for welding iron railway tracks together. Molten iron fills the gap. And a grinder makes it smooth.
So now that we've seen a few demonstrations, let's move on to our lesson sheet.